Hello everyone! In this video I will show you three operational amplifier circuits and their simulation in Proteus. For all of these circuits, the gain is set to exactly 1, with this to clearly observe the addition and subtraction phenomena directly on the oscilloscope. Our first circuit is a summing amplifier. As you can see in the simulation, multiple signals enter the circuit. Because the gain is 1 for each signal, the output on the oscilloscope shows the exact mathematical sum of the inputs. Now, as we can see this in the practical phase, all of the input signals has the same amplitude and the output signal is the sum of all of them. Now, let's move on to the second circuit. This is a subtractor. Just like the first one, the gain is set to 1 for every input. When we run the simulation and open the oscilloscope in Proteus, you can clearly see the result of the operation. The circuit takes one signal and subtracts the other. The final output wave we see here represents the exact mathematical difference between the two input signals. Building this in the laboratory brought new challenges. In the real world, things are a bit different because physical resistors have small variations and tolerance. The physical circuit requires very careful assembly to avoid noise. Despite these real-world factors, when we test a physical circuit, the output wave matched our simulation perfectly, proving that the subtraction was working exactly as designed. Finally, here is the third circuit. This one is a more advanced summing amplifier. In this design, signals enter through both the inverting and the non-inverting inputs of the amplifier. However, there was a challenge in the design. We want all the signals to add together, not to subtract. To fix this, the signals going to the inverting input must pass through an initial stage first. As you can see in the schematic, this previous stage is a simple inverting amplifier with a gain of 1, which simply changes the sign of the signals. Because of this extra step, when those signals reach the main amplifier, they add up perfectly with the signals from the non-inverting input. You can see this complete sum right here on the Proteus simulation. Translating this specific circuit to the breadboard was the hardest part because it requires more wiring and an extra operational amplifier stage. But the simulation served as a perfect guide. Thanks to adding that first inverting step in our physical build, the real circuit adds all the signals perfectly, just as Proteus predicted. In conclusion, simulating these circuits in Proteus is a great way to validate our mathematical design. But building the physical circuits with real operational amplifiers proves that the theory actually works in the real world. Thank you for your time and thanks for watching.